Y después voy a dar por la asociación. Okay, so we're gonna continue with the talk, the second series of talk. So just a little announcement. The last talk, the talk by Hayek Wittgenstein, is gonna be moved as the very last one. So instead, we're gonna have the poster session. So I just announced the poster that's gonna be presented after after the talk of Ana Maria Rivero. So it's going to be the poster number 1, 6, 10, 14, 15, 16, and 18. So get ready. Okay, so we're going to start with Teresa Huertas Frontal, who's going to talk about the millimeter survey of RLs towards sea-rich planetary model.
Thank you, Laurence. Hi, and thank you for being here. I'm Teresa Huertas Roldán, a last year PhD student at Instituto de Astrofísica de Canarias. And I'm presenting here our last paper with this very deep millimeter survey. Here you have the reference and also the link to the paper if you want to read it. So let's start from the beginning. In the evolution from the AGB star towards the creation of the planetary nebula, many chemical reactions take place in the medium. And at the end, we have many different molecular species. We can observe them in IR or in radio. In IR, we usually have bands. And here in this example, you can see 3 very different species, but all of them sharing the same bands. So you cannot detect unambiguously which species are you observing. In radio, we have lines, narrow lines. So we don't have any doubts on which species with dipolar moment are we observing. So with this in mind, our objective is to detect weak radio lines and find their carriers. We have observed these 2 carbon-rich planetary nebula. ICE 418 is a very well-known elliptical source with a very interesting content in radio. It has fullerene, for example, and in radio, only radio recombination lines have been detected. No signs of molecules as simple as CO. In NGC 7027, we have this multipolar shape with a binary system in the center and a rich molecular content both in IR and also in radio. The observations were made with the IRAN 30-meter here in Sierra Nevada and also with the Yebes 40-meter telescope. We observed these 3-millimeter bands, very long projects, and at the end we could reach an RMS of about 1 millikelvin. Why? Because we want weak features, and this is crucial. When we first had a look at the spectra, we found a significant number of radio recombination lines. So first, we calculated all the frequencies of light atoms using the Rydberg approximation, and we could assign each emission line with its corresponding radio recombination line. We did this in IC 418 and also in NGC 7027. And here in this example of the spectrum, you see the recombination lines, but also some molecular emission. Then we used Coral, a model developed by Daniel Tafoya, which allows us to model at the same time the set and an ionized 3-dimensional object with radio recombination line emission. We joined both results, and here we have 3 examples on IC 418, where we see that the model fits very well the spectral observations. And here in this planetary nebula, we detected hydrogen and helium radio recombination lines, some of them as weak as this one. In NGC 7027, the model also fit quite well the spectral results, and we found hydrogen, helium-1, and helium-2. And here we have an example of this species. So we ended with the largest radio recombination line survey up to date, with hundreds of detections in each source. Here you have the table, the details of this survey with every range and the number of lines corresponding to each species. Focusing on each source, this is the summary plots of the detections. And here you clearly see that the model fits very well the spectral results. Here on top, the hydrogen results, here the helium-1. We didn't detect helium-2 in this source. We didn't detect carbon-1 radio recombination lines, probably because of the low abundancy of this atom. We have also compared the full width half maximum values of hydrogen and helium, and we found that these values are quite different. So this could point that the expansion velocity of each species is different, and also that there is some stratified emission around the central star. Focusing on the physical parameters, all the parameters that we used in the model or are derived from the model fit very well with the previous works, except for the electronic temperature. We had to choose this higher value than in previous works to fit both the set and all the set of radio recombination lines at the same time. In the case of NGC 7027, again, this is the summary of the results. Here on the top, the hydrogen results, here the helium-1, and as I said you before, the helium-2 results. Again, we didn't also observe carbon-1 radio recombination lines, also probably to the low abundance in that area. We also compared the full widths at half maximum, and in this case, the values are rather similar. So we concluded that the emission is roughly from the same location around the central star. We found similar results if we compare with IC 418. All the parameters derived or used in the modeling are compatible with previous modelings and works, except for the electronic temperature, which in this case is quite high compared with results from the infrared and the optical. So yeah, here is the summary of our paper. We have found significantly high number of radio recombination lines, and these kind of lines are very important in the characterization of the chemical content of any source that we are investigating. These are the numbers of the detections, quite high, as I told you, and focusing again on each source, we concluded that IC 418 is really populated of radio recombination lines. We didn't find any evidence of known molecules, even the lightest ones, but we found some unidentified emission lines that we are trying to analyze and find their carriers. And this, about the full widths at half maximum, we think that the emission is stratified, but we cannot prove them without interferometric maps. In regard with NGC 7027, the medium is highly ionized, so we could detect radio recombination lines of helium-2. The emission seems to be not stratified as in the previous nebula. And in general, we found some problems with the electronic temperature. We tried to model the sources using the values in the literature, but it was impossible. We couldn't reproduce the peak flux intensities that we were observing. So this seems to be still an open problem, and we should try to find something to mix both the radio results and also the infrared and optical results. And yeah, that's all. Thank you very much for your attention.
Thank you, Teresa. So we have questions?
Very nice talk, Teresa. You know what I'm going to ask.
I know, because we have discussed it.
It's a little bit worrying for me that you found that such a large electron temperature. It may be a problem with the model.
I would say that the problem is not the model, because it has been tested in other sources and they didn't find any problem. But if you see the shape of this source, let me arrive. This source is very complex. It has also like 1, 2, and another one yet. It has also over here X-ray emission, and what we are observing is some area in this part. So probably this medium is very hot, and we are tracing that temperature. I have some extra slide comparing both temperatures. Yeah. So this is what I found in the literature. There is some ambiguity depending on the lines you are using, obviously, but it's significantly different. So maybe we are tracing the inner core, which is hotter than the regions where these lines were observed, I guess.
Maybe the 18700 Kelvin temperature, do you remember which diagnostic was used for that temperature?
These were ratios in the optical.
But which ratio, do you remember?
I don't remember. I remember the paper, but not the numbers.
Questions?
Yep.
Yes.
Thank you for the talk. Could this problem of the temperature be caused by shock excitation? Because on AGC 7027 there are no outflows.
Yeah, why not? I mean, here our data only recovers the total power. We cannot find the location of the emission. That's why we need interferometric maps. But yeah, that could be because we are observing that inner core of the nebula.
Continue the same point. How do you derive the electron temperature? Does it come from the line broadening?
The electron temperature is an input to the model. So we run the model several times until we got the peak fluxes that we were observing. So the first run was with these temperatures of the literature, and lines were like half of the emission that we were observing. So we increased the value until we got the results. And again, I would like to insist in this, the model fits at the same time the set and all the lines at the same time, all the lines together. So
including the line profiles?
Yes.
Yeah.
Yeah. So these plots are comparing these ones. This is what the model gives, the pink line. One of the outputs is the pink line. So yeah.
Any other question? Go ahead, I'll be back.
Since you mentioned getting interferometric data, I will say mea culpa. We have a complete 3mm line survey of NGC 7027 with NOEMA.
Okay.
But I don't know that it's going to have a sensitivity or necessarily the resolution that you would need to tease out the possible contributions to the electron temperature.
But
But it's worth looking at the archival data since it's too much data for me to deal with.
yeah, that would be super nice.
Thank you very much, Teresa.
Thank you.
Next speaker is Dennis Carlos from South. So she's gonna, the talk is about through legalization, correction, tax curves, care about PM legislation.
All right, thank you. Yeah, I'll start with what Joel said. Now that is too much data for you to deal with. For me, this project is too much models to deal with. So, and you understand why. So I'm again talking about the ionization correction factors. If they have something to do with the change with the morphology of the planetary nebula. And the reason I can talk about this here now, it's because this master student, he dealt with all the models to get the recipes, I mean, the formula you need. So the thing is that, let's put here some definitions, is that, of course, you know very well, a spectrum of rage planetary nebulae with numbers of lines and the way they are produced. And we see here, different ion fractions of, nitron. You see others as well, but those we'll deal with here will be nitrogen, oxygen, neon, sulfur, and argon. And so we need this definition because you see some formulae later. And this is the ionic abundance of a certain element. It's related with the intensity with relative to the ionized hydrogen, sorry, and the intensity, the rate of the case of the two lines and the emissivity of these lines. Another important thing is that whatever I talk here, it will be about the optical spectra of planetary nebulae. So from this range you see here. Then, of course, if that is the ionic abundance, to get the total one, we need either to observe all the different fractions in the optical spectrum or find a way of correct it for those we don't see. So the thing is here you have the definition of the ICF, that it's this correction, that it related the total abundance with, the sum of all the ionic fractions that you do observe. So this is a multiplicative factor that you put there. So of course, to get, reliable or well-determined abundance, they depend crucially of these ionization correction factors. So how do you do this work? You have a number of models, and for this, we were using the Moccasin, that it's a 3D photoionization code that deals with the equilibrium, solves the Serral and ionization equilibrium of the gas. And he does this in a 3D fashion. So we have the distribution of mass here, characteristics, for the parameters, luminosity and effective temperature of the central star, and the nebular things, the density, the shape, and so the morphology, density, and also the abundance. And in fact, what we simulate, it's not the whole structure like this, but a octant of these, and then use the symmetries to get the rest of the nebulae, And they try to represent these three kites, only these three, with only one way of representing, because otherwise it's even much more models. And here we decided for this tree based on the statistics of the observed nebulae. Those here I'm trying to show all the parameters that were taken into account, and these are the parameters these two for the central star. So we have this range of temperatures that is characteristic of here, of course, the chart diagram for the central star or planetary nebulae. And also we put here, based on this catalog of the central stars, the values here to decide which are the models that are really representative of the planetary nebulae. This is for the central star, but then, then for the density, use these three values. Then we enter 6 times as much of these values for the torus if it's a bipolar model. Then 2 different abundances that are defined like this by Kingsbury and Barlow in 84. And of course, this is the number and the observed ones in hash catalog, the round, the ellipticals, and the bipolar planetary nebulae. We saw this morning that's probably this is not really true. Then we realized when comparing our results with the results of other people that did the ICFs, the last one, for instance, Delgado and Glada, that you should increase the temperatures for going much higher here, and also include the chlorine that we didn't in the very beginning. So we still didn't do even more models. But the important thing is knowing that the gas of the planetary nebula and also the central stars are well covered in these models. Then after times working with the ICFs, we realized that instead of directly use all the models to try to fit the recipes, if you'd use, based on this paper, the excitation class of these models would make things far much easier. Then what you use is this classification for the excitation, and this is the high excitation models and the low excitation one. And we see in this distribution, we see here, it's based on our models, not in this paper, but this is the way our models are distributed more or less. So most of the models are in high excitation. And as I said, this is important to fit much simple recipes. Then another thing that they did that similarly to the work, the nowadays most used recipe for the ICFs, we defined 3 variables that, the first one has to do with the luminosity of the planetary nebulae, the second one, let's say, the effective temperature, and the third one here, it's for the case in which this one is too small. In fact, it's already too small because of this right here, no? And here we see how the models are distributed in terms of excitation, in terms of the excitation, so the low and high excitation. Here is the temperature, here the luminosity. And another important thing is that whatever emission line that you use for these recipes, they need to be at least 0.5% of the H beta. Then I want to talk about one of the cases, because there are many, I cannot talk about all of them in 40 minutes. So I use nitrogen as a illustrative case. So what you do here, we take the 4 bright lines that are collisionally excited, and then you get, in the optical node, then you get the ionic abundance for these 2 fractions. And it's important to look at here. These are the 4 lines we are talking about. In this one, in fact, in most of the spectra I have, we do observe this one, but it's not always. And you see that for the low ionization, low excitation, guys, you not have this line. You cannot consider this line because of this threshold. And then you have 2 cases, so 3 cases in all. For the ICFs for nitrogen, it's the one of the based on the high excitation models. In this case, you can use these 2 lines or only this one because of this exception here. And then in the case of the low excitation models, we only observe these species. So, and another important thing is that the other ICFs that are available, they do not take into account this line. Then here we see the results. Here are the ICFs we get for the first of the cases. Here, based on these 2 ionic fractions. And here is the distribution of the ICF data points for rounds, elliptical, and bipolars. Here, we have the second case of the high excitation, which this line is not observed, but only that one. Then here, I have a gift. You cannot see the whole structure here because it's a PDF. But anyway, of course, you have, based in these, the 2 or the 3 variables we define, and have here the distribution of the data points. And from that, you get the ICF. So we see that ICF, in this case, the nitrogen for the high excitation, in which you get the 2 lines, is this one. Of course, the value of the parameters becomes later. And for the other case, it's similar. Note that in general, the round and elliptical have very similar results. So I'm showing here only ellipticals and bipolar. Thank you. Then you see here for the same models, nitrogen again, but here it's a result for the bipolar. In terms of the distribution, if you want to go back and see, they are similar here, except for, small difference here, they're similar. Then what you get for the bipolar case, it's these two fits that are different, significantly different from the rounds and ellipticals. Then for the low excitation case, we have only these lines that can be observed, and you see this is the distribution of data points and the 2 formally get. So in our the results have this kind of definition. Here are all the definitions for nitrogen and all the values of the constants that go in these definitions, and also the uncertainty based on the user models to get these results. You have this for nitrogen, but as well as helium, oxygen, neon, sulfur, and argon, and I'll not show you here. The minimum test you can do with this is to see if you are able to recover the input value of the abundance. And this is what you do here for the high excitation, low excitation models. And what you see here is that, of course, the right thing, or the thing you would like, is to see that all these distributions are centered here in one. And this is, well, they're not too far from this, but it's not really one. So this has to do with these values, but the uncertainty of the method is these values you see there. Also, we see here that the distributions are different for the different morphology. Either doesn't matter if in the high excitation, low excitation case. So as in the latest ICFs, Delgado and Glada 2014, and collaborators, uncertainty are very relevant. Then another important thing to do is comparing these with the 1D cases, the ICF is based in cloudy model, photonization models, and we compare with the two recipes that are the most used. In this case, so what you have here, you take the ICFs that we derived, then you also use the models to obtain the ICFs following the recipes in Kingsburg and Barlow's 94. And then you have here the data points that it's rate of these two values. I mean, the discrepancy between one and another of these ICFs. And you can fit corrections for this. And this in all the cases. So this means that in the case of using, if, for instance, you have your results using the Kingsburg and Barlow ICFs and you want to correct for morphology, you can use solutions like this that you did, because you can find further corrections based on the morphology only. And in the case of Delgado and Glada, this is much more complicated to do the same comparison, because they give ICFs in terms of not hydrogen, but rates with the abundance of the different elements for the rate in between the different elements and oxygen. So it's much harder to compare. So the comparison we do here is to see if you use their recipes or ours, we see what you get at the end in terms of the nitrogen. We see that they are more discrepant than in the other case, but anyway, within 10%. And okay, and I'm finishing 1 minute. So in this case, the only way to take into account the morphology is recalculating the abundance. But remember that you have the same definitions for the variables. So it's very easy, because you have that variables there in your data. As I thought I will not be able to talk about this. And I go to the end, that it's our conclusions and things that you want to do. The first thing is that, yes, the ICFs change with abundance, and much with abundance with morphology, and much more for in between the bipolar, much more for the bipolar than for all the other two morphologies that you tested. The other thing is that it's possible, I mean, and this has to do with the fact that the diffusion radiation is much better treated in 3D than the 1D. And the other thing is that you did a lot of effort to be able to further correct the abundances that you have from Kingsburg and Barlow's recipes for morphology using this data show. In the case of Delgado and Glada, again, you need to recalculate, but based in the same variables, so it's kind of easy. And then the things you need to do. We need to evaluate the impact of the atomic data because we are using Moccasin and the atomic data in Moccasin emit that they have the same, but this is different from PyNap, for instance. So you need to test against these two. There is something that it's really important. We are now evaluating this. Moccasin has no good solution for iron, and iron is important, cooler. So this is something to do. And even more relevant, you wanna grains. Dust grains are not included in our models. And at the end, you need to test this with sample of quantum average. So we still have a number of things to do. Thank you very much for it.
We have questions. Hey, Dave.
Thank you.
Hi.
So ICFs, maybe this is a really naive question, but they're valid for the integrated flux of the entire nebula, right?
It's naive and important. Yeah.
So if the morphology is so important, then given that most of the data we have is long slit that covers only a fraction of the nebula, then the orientation or the position of your slit should be just as important as the morphology.
Yeah. The things that for years we are thinking about when you finish this work that it's considering that or observation the whole nebulae, then you can try to do something similar for spaxels, no? And in fact, you can compare with news data and other data with high spatial resolution, let's say, and then understand what happens because a number of people here have working with spatially resolved abundance. And this is really hard to do because the ICFs have nothing to do with this. We are getting things completely wrong if you use even those ICF to understand what happens, spaxel by spaxel in a planetary nebula, for instance. But if these ones takes around 10 years more or less, or more than this, they think, we need more hands to do this work. But it's true, it's really important to take into account the orientation of the slit or, this is not a spatially resolved design.
No questions? Thank you.
Nice talk, Denise. From what I understood, the agreement of your ICF with the previous ones is better when you deal with low excitation objects, in the case of nitrogen, than when you deal with high excitation objects. That makes sense, because
Makes sense because
the classical ICF is nitrogen over oxygen is equivalent to nitrogen plus over oxygen plus.
this is one of the reasons. The other one is that for the other classes, we're also including the 5,200 salt neutron nitrogen, and they are not in the other recipes. And then, this is part of the reason as well.
And another comment, you say that you were going to check atomic data because you find that the PyNeb atomic data, are different than the Moccasin one. You can change in PyNeb atomic data very easily. You can put exactly the same set than in Moccasin and check if everything.
This we didn't do yet, but we want to do it. But the important thing is that our ICFs are based on Moccasin. So we have those atomic data there. But what happens, what is the uncertainty at least that you get if you go to, at least for those that are available now, different atomic data, because there could be difference there. In the case of the Garden Glada, for instance, they use it all the time, clouds. And then when they doing all the tests they do in the paper too, all the tests they do, they're using exactly the same data, atomic data. And you'll not be able to do these two recipes that are in the literature. So it's important to add this in the discussion.
Okay.
Thank you again. We have Ana Montreal Vero. So Ana is going to talk about the Planetary Nebulae Survey with news.
So welcome everyone.
My name is Ana Monreal Ibero, for those of you that doesn't know me. And I would like to thank the organizer for giving me the opportunity to present the work that we are doing in the context of the PLANS program to study planetary nebulae with MUSE. I say we because this is a team effort and everybody that appears here is contributed in a way or another. But I would like to mention in particular Jeremy Walsh involved because I consider him like a spiritual PI of this project. So we are going to start by the very beginning, which is, I will say, a summary of what we have seen this morning. When you take a book of interstellar medium or ionized nebulae or even stellar evolution, and you go to the section where planetary nebulae are described, you will reach to a piece of text or perhaps a teacher that describes planetary nebulae with something similar to this sketch. The point is not here is not explaining all the different labels that are in the slide, but pointing out that this is a structure relatively simple, spherical, and like an onion. Yet, when you go to the reality, you find something like this. We see that there is a large variety of planetary nebulae. They have different sizes. There are some that are spherical, some that are bipolar, multipolar. Some of them present small-scale structures. And to understand this kind of objects, we need somehow to capture this complexity. We need other things too. And to capture this complexity, we need a comprehensive information, both in the spatial and the spectral direction. In my case, in the optical, because it is where I work the most. And because of this large variety, it is not enough with studying only one target. We need at least a sample of an acceptable size. And this is where integral field spectroscopy comes to the rescue. We cannot say anymore, I will say that this is a new technique. The letter with the VIMOS IFU was in 2005, so that is 20 years ago. 20 years, wow. But I think it is in these years where this technique is becoming of general use also in this community. And I hope that I can show with this example the kind of wonders and the kind of surprises that you can get with this technique. This is not the only example. There has been several others in these 20 years. Some of them actually will appear in this meeting. I think we have 2 presentations later on this afternoon. Another one on Wednesday, Jorge, you are there. There is also a poster, Jan is there. So, but this is a very valid example to support the formula that I have put there, that comprehensive coverage, spatial and spectral coverage, plus depth can give us surprises. This is the nebula that I am using to support this. This was observed during the commissioning of the instrument, and this is the area that was covered. This is a high excitation nebula that emits very weakly in low ionization lines, and so far there was not nitrogen detected in the nebula. And I put this sentence in orange, so you have a not subtle at all hint of what is the result that is coming. And the results of this work is in this reference that you see in this corner. So let's have a look to the nebula in different emission lines. These are the recombination lines. This is how the nebula looks in H beta. Most of the helium in this nebula is 2 times ionized, and actually the structure of helium-2 and helium and H1 is almost the same. This is the ratio of an helium-2 line and an H beta, and it is almost flat. And only in the corners, helium-2 starts to recombine to helium-1. When we look at collisionally excited lines, here you have 2 lines that comes from 2 different ions. This is argon 5, argon 3, high ionization, lower ionization. The structure is different. Here it looks more like a horse shoe. Here, to me, it reminds to two lungs. But in both cases, the structure is relatively smooth. When we look to medium ionization lines, the structure is pretty much similar to this one, which is not a surprise. So what about low ionization lines? So this is what you get when you look at nitrogen 2. There is a plethora of nodes that emit in nitrogen. And what is, we detected more than 100 of these nodes all over the nebula. And what it was more interesting is that even at the relatively poor resolution of MUSE, it's not that poor, we were able to see that all these nodes are kinematically decoupled from the main movements in the nebula. Here. We discussed possible origins for these nodes in the paper, but this talk is about surprises. And this data cube actually came with a bonus surprise, which is that when we were looking to the data cube, we noticed that in certain portions we were getting a set of emission lines that was systematically shifted towards the red. And actually that corresponded to the HU regions that were in a background galaxy. Of course, you can model with care the nebular continuum, subtract that, and then you are left only with the continuum that corresponds to that background galaxy. So we were able to find or characterize more or less the galaxy. This is how it looks like for the stars, and this is how it looks like for the HU regions. So I hope that with this example and others in the literature, we were convinced that integral field spectroscopy can deliver surprises and interesting results. I hope that you are convinced now too. But to assess the prevalence of these findings in planetary nebulae as a population, it is not enough with studies on one individual target or very few targets. So we thought that it was the time to move to studies based on samples. And with this spirit, we applied for MUSE time, and we continue applying to obtain observations for a sample of 10 new planetary nebulae that together with those that are on the archive, you can gather, let's say, a sample of around 20, 25, depending on how much quality you want for your data. So the global goal of the project is unveil the hidden complexity of planetary nebulae. And in what is left of this presentation, I'm going to show a preview of what you can obtain with this data using the cube for one of the nebula that has already been completed with full observations, NGC 1868 and 18. Remember, we have this formula: comprehensive spatial and spectral coverage plus depth can give us surprises. This is how the nebula looks like with MUSE. This is an RGB image. RGB means red, green, blue. And this is made from the MUSE data. And look that we are able to see, is it in logarithmic stretch? So we can see the main nebula, but also the halo. And I am not sure if you can see, but it is possible to see even the rings of the halo, okay? So the quality is really, really excellent. In the next two slides, I'm going to discuss only the main nebula, and I'm going to present this portion of the nebula that corresponds to the orange square, and that here is presented in linear scale. So this is how the nebula looks like in some of the mission line maps. This is H alpha. This is a low ionization line, and this is a high ionization line, argon 5, with an ionization potential for the emitting ion of 60 electron volts, so it is really quite high. These structures that you can see in nitrogen, they were already known. They are called mustache in the literature and others. For the high ionization line, the structure is relatively regular, but not fully spherical. there is less emission towards the north and the south. But remember that under certain conditions, Muse can also provide useful kinematic information. And this is very well seen in this plot where we see how different is the velocity map that we get from the nitrogen lines from the velocity map from H alpha or argon phi. So yes, sometimes we can learn from the kinematics. Now comes the surprise. This is not the line coming from the ion with the highest ionization potential. We found and map emission lines with coming from ions from even higher ionization potential. If you look here, iron 6, iron 7, with ionization potentials that are already in the domain of the coronal lines. For me, that was the first time that I was seeing these lines. And systematically, in all these lines, we were getting this structure elongated from the northeast towards the southwest. And also, very important, we are fitting these lines independently. And when we were looking at the kinematics, all of them, they were presenting this gradient from red to blue of about 30 kilometers per second. As for now, the interpretation that we are working with is that this is consistent with an inner bipolar jet in the nebula. And we are super excited with this research. Okay, I have 3 minutes to finish. Before going to the conclusions, I would like to make a commercial break. Yes. We will have soon an opening for a position, hopefully next week, for a PhD position to work on this data. I cannot offer a lot of sunny days. I cannot offer high mountains, but I think I can offer a very exciting project in a very nice environment in one of the best institutions of the world. There are no students that cannot apply. Hopefully they can start applying next week. So if you have good, excellent master students that want to continue working on planetary nebulae and would like to move to the Netherlands, encourage him or her them to apply. And now I'm going to move to the conclusions. The main scientific conclusion of this presentation is included here. We have found emission in coronal lines, up to 10 coronal lines or so in NGC 6818, that it is compatible with an inner bipolar jet in the nebula. But I would like to zoom out and put in as takeaway messages some more general conclusions, let's say. First, the formula, comprehensive spatial and spectral coverage plus depth can give you surprise. We are in the right time to move from works on individual targets to works based on samples. There is an opening position in Leiden, and stay tuned for more surprises. And that's all I want to tell you. Now is my time to take your questions. Thank you for your attention.
We have questions?
Very nice talk, Alan. I have a question regarding the Muse data of NGC 68. When you detected the coronal lines, have you detected recombination lines of metals in this spectrum?
So you are not asking about these particular lines. We have detected, I have forgotten the number, somewhere between more than 100 lines and less than 200 lines, perhaps say 150. I cannot remember by heart the 150 lines that we have detected. Perhaps we can check later on if the line that you are interested in has been detected or not.
No, because I'm saying that because in my talk I have also surprises, and we have something related to that, and maybe it would be very interesting to check that in that set of data.
Maybe
Ask Roger.
Maybe we have checked that. Maybe it's already in my computer, but yeah.
Okay, thank you.
Question?
It was really a very nice talk. You said surprises. This is really a surprise. Is there any other that you should expect from this data that you have? In addition of this?
If I am expecting that, it's not a surprise anymore.
No. Oh, another object that coming with surprises as, you know, spectacular is this one in your sample, because this is one. One of
Well, the purpose, I want to hire a PhD student to work on the data, so I don't know yet what I am going to find on the data. But here I presented an old example and a new example, and both came with surprises. Yeah.
So excited this for yours. Thank you.
Okay, so if not, we will thank you. Okay, so I said at the beginning, so the next stop by R.S. Einstein is going to move at during the last one, actually, the last one of the next session. And now we're gonna start with the poster presentations. So I think it would be better if everybody's coming there. So poster number 1. Okay.
Because I was just trying the website to register, and this is why I have the poster number 1.
Poster number 6, number 10, 14, 15, 16, 18.
Valeria Beltrán, 16 somewhere dog. Yeah. Nicolas Clark, over a few. Castillo, Chesler, and Jaroslav is here. Candy Bad.
So,
Okay.
so you have 2 minutes.
2 minutes. Okay, try to be fast. So this is a work basically that Roberto Ortiz and I we have been doing for a long time, working on X-ray emission from AGVs. And now we decided that we need help. And so there are more people like Jesus, Jaroslav, Rudy, Joel, Diego Alejandro, and also Janis helping us with this task. So I'm summarizing here 3 different papers that we have published. The first one is a survey of the IGROSITA catalog. So we've cross-correlated catalogs of AGV stars with IGROSITA. And we found, together with a previous paper by Smith, and that we made some corrections there. So we basically doubled the number of X-ray AGV stars. And those are now increased up to almost 50. So you can see here the cross-correlation between the X-ray images and the optical. And we have to take into account that IGROSITA could be affected by optical loading. So the question that we found here is that some symbiotic stars, they have like similar LX luminosity and ultraviolet luminosity to some of the AGV stars. And actually, the brightest, so the symbiotic X-ray stars are significantly brighter than the X-ray AGVs. But there is an overlap there. So you cannot really, by the X-ray properties, tell whether this is symbiotic or whether this is just an AGV star. And so we started looking for some features that telling us whether these AGV stars are really symbiotics. And indeed, we found here for Y Geminorum that there are some emission lines that they correspond actually. So here is, so you can see the O3 line. There is also H alpha. And so we see that there are forbidden lines that are telling us that there is a hidden white dwarf there. And so those are the pulsation period of the HB star, and those are very long period that could be related to a white dwarf in the system. And we also did the same for CGS-6306. So here again, we were able to find emission lines that can be attributed to a white dwarf. And so this is the X-ray emission. So basically, we think that there is a hidden population of X-ray AGBs that are actually symbiotics, maybe working on a different regime. Thank you.
Hi, so we did a high resolution spectroscopy of the bipolar planetary nebula, well, protoplanetary nebula, Genais. Yeah, a lot of you have studied it, and we found some like funny things. ¿Cómo hacerlo más grande? No sé. Bueno, well, essentially, we found like these bumps in helium lines that hadn't been reported before. So this is like very interesting because we have like a very high resolution data, and we have like a full line table characterizing this object. We also have like blue velocities from all the Persigny lines that we found. We also did a study of the knot. This is an object that has a lot of knots. So we did some of this, and we found like different things that from 20 years before that it's public data. So we also have like a change in profiles like from 20 years ago and now, and this is some of the spectra in O lines. This is 63, but we also have like a lot of more plots. So like this is essentially what we did. No. This is like the full spectra. So that's kind of the idea of what we did.
So protoplanetary nebulae, thought to be precursors to planetary nebulae, and for 35 years or now, we've understood that also many of them are very strongly shaped and seem to be the result of common envelope evolution. Recent studies, theoretical studies, have shown they're consistent with energetics and shaping from common envelopes. Well, those of us who study close binary central stars post common envelope binaries have started to understand for a little while now that they don't seem to be consistent with protoplanetary nebulae. So Bruce Ribnack's talk tomorrow will talk a little bit about some of that evidence and looking for binaries in protoplanetary nebulae. But what we've found is we've done sort of a brief literature review of the properties of protoplanetary nebulae, what we understand about common envelope evolution and the properties of close binary central stars, and found that they're just not consistent. So protoplanetary nebulae do not seem to be the progenitors of planetary nebulae with close binary central stars, which then leaves a lot of questions about what do they end up as, what part of the common envelope are they going through. So this is essentially just a review demonstrating that they don't appear to be consistent with being the progenitors of close binary central stars and planetary nebulae.
Right. Hello, everyone. I'm Nicholas Clark. I'm a PhD student under Drs. Els Peters and Jan Kami at Western University in Canada, and I'm here to talk to you about PAS in the Butterfly Nebula. Now, the Butterfly Nebula is a bipolar planetary nebula with a complex morphology. If you want a more zoomed out picture of it, you can look at the booklet. And it's notably oxygen rich. So at first glance, you wouldn't expect to find much in the way of complex carbon chemistry, but fortunately for me, it is rich in PA emission, among other carbonaceous species. Now, PAs, or polycyclic aromatic hydrocarbons, as the diagram over to the right shows, consist of fused benzene rings. They emit very strongly in the infrared, so they're perfect for viewing with JWST. And when we did this and looked all around the Butterfly Nebula, we found there was significant variation in the emission characteristics of the PAS. And this indicates to us that there's actually processing of the PAS occurring within this object, which is the first time we've ever seen such a phenomena. So if you'd like to learn more about this exciting new finding, you can come. I encourage you to check out my poster. And thank you for listening.
There's the switch.
Yes.
Okay. Hello, everyone. My name is Jaroslav Merz, and as you will see tomorrow, my main field are symbiotic binaries. This is not a symbiotic binary, but it was remote. There was a remote possibility of being a symbiotic binary. So therefore, I was interested in that object. So if not, that's in my paper from 2021. So that's not new. But what is new is the data that we collected. So first of all, we have now the nice image, which I'm happy because my symbiotic papers doesn't have typically, nice images. And in this nice image, it's 56 hours of exposure, 57 almost. So in addition to this middle part of which was known before, we detected this very large structure that was not known before. So the central star is somewhere here, and the two things that I will discuss here, because 2 minutes is amazing for giving all the information about this interesting object. So first of all, the central star of this planetary nebula is a multiple system. So there is a UV source which coincides with the K-type dwarf star, but there is a third component which is here, this one, that is revealed by proper motion and parallax from Gaia. The thing is that this system is actually moving in the correct direction with the conical tail in the opposite direction. So we know that this is associated with the nebula. The other thing, what we did is to observe a lot of data, and there are also survey data, what you can see here. So this star is showing very interesting variability. This is 21.3 days. It's not orbital, that we know. It's stable for 10 to 25 years. The amplitude is largest in blue. We did the RV monitoring, so we don't know that it's not orbital. And the explanation that we have that seems to work, which is still weird because of the stability, is rotational modulation due to spots. And I will not tell more at this point. Check the poster, talk to me, and stay tuned for a paper. Thank you.
All right. Hello, everyone. My name is Charmi Bhatt. I'm also from Western University in Canada. I work with Jan Kami. I don't want to stand between you and your coffee break, so I'm going to make it quick. As Nicholas mentioned, the JWST MIRI instrument observed the central region of the Butterfly Nebula, and it turned out to be very interesting because we saw spectral signatures of CH3+, and it becomes the first detection of CH3+ in a planetary nebula. And it's very exciting because now we get to expand our chemical networks and include all the reactions which are facilitated by CH3+. So that's very interesting. If you come to my poster, I would love to talk to you about how the CH3+ emission changes with morphology, what new things we found about morphology with the MIRI data, and also how the spatial distribution of CH3+ compares to distribution of other carbonaceous species. So see you outside. Thank you.
So, thank you. And we're gonna see at the. No, yeah. Please. So we're gonna thank again our. So if you have questions.